Interfacing the MPU-6050 with an Arduino today on Mikey's Lab. Hi, and welcome back to the lab. If this is your first time joining us, go ahead and click that subscribe button down below to make sure that you don't miss any of our videos. Today we have kind of an introductory basics sort of video. We're going to be talking about the MPU-6050. So lab code up. We're going to learn something today, which is a 6 degree of freedom accelerometer and gyroscope. Now what this means is that this particular device will feed us degrees per second rotation and g-forces on all the x, y, and z axis. Now this is going to be one of the main sensors that's inside of the rover that we're building. However, there are lots of traps for new players. And when I did look up the resources on the internet for how to use these with an Arduino, it became painfully clear that most people who use this are not programmers. So what we're going to do is we're going to take a step back. I'm going to show you how to hook it up. This is going to be part one of a two-part series. In this part, we're going to get data out of the sensor. We're going to learn how to calibrate that data so that we're at a base level and we can deal with the noise that we're getting. And then in the second part, we're going to look at using that data to come up with a relative angle for roll, pitch, and yaw. This is the same sensor that's used in a lot of flight controllers for drones, so I know it's really capable, and I'm looking forward to working with it. So let's take a look at the bench and find out exactly what we need to be able to do this. Also, when you first get the sensor, it's going to come in a bag like this. It's going to have two sets of headers inside of it, a straight header and a 90 degree header. The one you choose is important because that can change the axis at which the sensors read from. They're fixed. So if it's not laying flat and in a specific orientation in your craft, then you're going to have to translate in software so that you can understand which way this thing is actually pointing. If we take a look at the board, you can see what I'm talking about. And you can see that X is labeled this way and Y is labeled this way. See if I can get you a better look at that. And obviously Z is up and down. Okay, so to follow along with this experiment, you're going to need an MPU-6050 breakout, like I have. I've also soldered one here. You're going to need an Arduino. You're going to need a breadboard. Going to need a couple of jumper wires to connect the I2C bus back to the Arduino itself. Alright, so what we've done here, we've hooked up the SCL and the SDA, so clock and data, of the MPU-6050 into pins A5 and A4 respectively. The A5 and A4 pins on an Arduino are your I2C pins. They're built in, they're part of the hardware, they're part of the wire library. So those are the ones that we have to use for this particular device. Now I have left a pin called AD0 floating. Internally it's tied to ground. AD0 is kind of a trap for new players if you haven't read the data sheet. Pulling AD0 to high will cause the address, the I2C address of this device to change. This is how they intended you to have two on a bus at once. It causes it to change by 1 bit so that you can talk to two of them at the same time. Leaving the AD0 not connected will pull it to ground internally, and it will have a definitive address that way. There are tutorials out there that say you should pull it to ground manually. I have not, and I haven't had a problem. Okay, so let's go ahead and dive over to the PC here and take a look at the code that we're using. The hookup is very simple, as I said. Alright, so here we are at the PC itself. You can see that I have the serial monitor open right now. The serial monitor itself is just spitting out the temperature in degrees centigrade. If your module does have a temperature part to it, this will display what the current temperature reading is. My breakout board does not have a temperature sensor with it, so it currently says 0. The next set of readings is gyro degrees per second. Right, as you can see, there is some wobble to the values. I'm working on purifying those a bit more, but they're fairly minuscule at this point. So you have X, Y, and Z. It's showing 0 degrees per second on all of the rotations. Then we have the accelerometer readings, which are red and G. We have X, Y, and Z. You can tell that the sensor is not perfectly level because all the time on Z there should be at least 1 G. In my region, for some reason, every accelerometer reads about 1.8 or 1.08 G. Gravity is working on the sensor. Gravity is affecting this sensor at all times, so it is being pulled towards the Earth at 1 G. This is good later on. You can use this with your perceived rotation to determine if you're right, because the roll and pitch of your device should cause that 1G, if not moving, to be spread across the 3 axes in a very specific relationship. This is something that we'll talk about in the second video a lot more, and it's kind of an interesting use of math. So now that we've seen that this code does work and that it does run, let's go ahead and drop into the actual Arduino interface, and let's talk about the code. Okay, so the first thing, this code will be available from the mikeyslab.ca website. As soon as I get the write-up done and posted, it will be there. You'll find that it's a little different than what you find in a lot of the other articles, but you'll also find that it's inspired a lot by it. So let's dive down and take a look at it. So the first thing we notice with the code that I'm showing here is a bunch of defines. Okay, first thing we're going to define, I define this in almost every Arduino sketch I use, which is pin 13 as a status pin. In most Arduinos, including the Arduino Pro Mini, there's a little LED that's on the device itself that is tied to pin 13. This makes it very easy to use this for status and to flash statuses back and forth when debugging. I use it all the time for that. I'm not the only one. Next thing we define is the register that we need to talk to set the power mode of this. I should probably preface all of this by saying this is a very complex sensor. The way that you deal with this sensor is to read and write directly to areas of its memory that are known as registers. The I2C handles all of that communication for us. We select the register that we want to use, and then we either send a read or write command from that register to either write data to it to have the sensor behave a certain way, or we send a read command to have the sensor send data back from whatever is inside that register at that point. This is a unique way, but it is definitely found in the higher end type of sensors and the stuff that is a lot more complicated to deal with. So when we're working with the registers and when we get to the actual code, I'll touch more on how these registers actually work. Just understand that a register at this point is just a place to store a value. So we're going to define that the MPU's power register is 0x6b. Now if you've never worked with hex before, this value is going to look a little strange to you. Hexadecimal being a number system based on 16, I'm not going to go into depth as to how to work with hexadecimal and how to understand hexadecimal and how to convert back and forth between them. There are plenty of tutorials out there on that. I'm sure you can find a resource that will help you out. The next thing we're going to do is we're going to define how we want the power for this module to run. In this particular case, sending all zeros in a byte, representing 0b is a representation of a binary value, as opposed to the 0x, which is a representation of a hexadecimal value. Now normally I would have stored this as a hex to write it through, but I figured since we're using flags inside of the byte, explaining it wise and making it clearer to read, this becomes much easier. It also makes it appear the way that it is shown in the data sheet, which again helps with the translation from code to data sheet to code. I'm going to set a global timeout of 2 seconds for a read. Okay, now this will come in a little bit later and be explained a little more later, but the 2 seconds means that if I send a command to read from the MPU-6050 and it doesn't respond in 2 seconds, we're going to give up and we're going to move on to the next reading. I also set the sample frequency to 250. Now 250 is a bit of a magic number. Well, not really a magic number. I hate magic numbers. 250 is the frequency at which this board is currently set to update its internal measurements. So every 250th of a second, it takes new readings for the gyroscope on all 3 axes and the accelerometer on all 3 axes. When it comes time to bring this into more usable data, that will be very important. Now, looking at the gyroscope values itself, the configuration register. Okay, this is the register that we write to tell the chip how we want the gyro to behave, what sensitivity range we want, and etc. We'll get into that all in a couple of minutes. We write that to this register, which is 0x1b. Okay, we set the other register up in the define for read as 0x43. Now, what this means is that when we ask for register 0x43 and issue a read command for how many bytes we want to read from this chip, that is where we will get the data from this chip into the Arduino. So then we're going to go ahead and we're going to define the MPU gyro read registry size as 6. This is 6 bytes. Okay, so when we read from the gyro, we're going to be reading a total of 6 bytes. The first 2 bytes are one axis, the next 2 bytes are next axis, and the last 2 bytes are the last axis. This is very important when it comes to put this information back together after. This next section right here, we're going to come back up to the main camera to talk about this. When it comes to using the MPU-6050, kind of a little bit of a trap for new players, but it's one of the features of the sensor. There is a scale that you can set in this sensor. The lower that scale, the more accurate the readings are going to be, but the less it can read. So if we take a look at the code here, you can see that I've got to define for 250 degrees. So the first level of the scale of the gyro on all 3 axes is a 250 degree per second maximum rotation it can read. This level will give you the most granularity to the reading. However, if you're going to be rotating more than 250 degrees per second on any axis, then you got to go higher. Okay, the other values that they have are 500 degrees per second, 1000 degrees per second, and 2000 degrees per second. Now, I can tell you from experience, this sensor, as I mentioned, is used in flight controllers, and 250 degrees per second just is not going to cut it in a flight controller. However, in the planetary rover type situation that we are using it for, 250 degrees per second is fine. The only way that I'm going to have a rotation higher than 250 degrees per second is if I fall off the roof. I'm currently rolling down a hill. It's about all I can think of. So I'm going to assume that 250 degrees per second is the maximum, and we are going to use that particular scale for our gyro. So for our example, we're going to ignore several of the defines here. It's these ones right here, which I put in place in case you wanted to use them after. But for our purposes, we're going to stick with just the standard 250 degree per second scale. The next define that I have is a calibration reading number. One of the ways to calibrate this device is to take a bunch of readings, find out how far off of 0 it is while the device is flat, and then use that to calculate back to 0. We will be doing this, and I'll be going over how to do this a little later on. But this define tells us that I want 2000 readings when we calibrate. So when the sensor powers up and the Arduino powers up, it's going to take 2000 readings from the sensor. And then it's going to calculate an average distance from 0 on all three axes so that we can use this later to re-zero the sensor. As I said, if your particular MPU-6050 happens to support a temperature sensor and have one, this is the read register and the size of the read in order to get the data. As I said, the one I'm working with does not have it, but I wanted to show you how to do that in here too. Okay, so everything we just talked about with the gyroscope is pretty much present with the accelerometer too. The scales for the accelerometer are 2G, 4G, 8G, and 16G. We're going to stick with around the 2G mark because we're not going to be setting any land speed records with our rover, and this will give us the most granularity. The other thing to note is that the configuration register for the accelerometer is 0x1C, and the read register is 0x3B, and just like the gyro, it is a 6-byte register. Okay, so the last two defines we really even need to concern ourselves with. MPU-1_I2C address and MPU-2 I2C address. As I mentioned earlier in the video, there's a pin on the breakout board called AD0. If I set AD0 to high, the address of this board becomes 1101001. If I leave it not connected or I pull it to ground, it's going to be 1101000. Now the purpose of this is so that you can have two of these devices connected to a microcontroller. Potentially so that you can verify the results that are coming out of your device. So if you have two of them, if they're massively out of sync, then neither can be trusted. Now there is a trick to use 3, which is kind of neat, and in mission critical systems I probably would use 3, where you have two that agree and one that doesn't. You know which one to ignore, and then you can go so far as to recalibrate the one that doesn't seem to be accurate based off of the known good values of the first. Alright, so now that we're out of the defines, I apologize, I would normally shove those in a header file in a CPP. Given that I wanted to talk to you about this, there's no real good way to do that with the Arduino. So the only include that we have for this program is include wire.h. What wire.h is that wire.h is the internal library for the Arduino to be able to use I2C. It just makes life a little easier for us. Yes, I'm aware that this sensor does have libraries available for them, but I hate black boxes. So let's take a look. We're writing our own from scratch, and we're not going to use the libraries that are available. If you want to, by all means go ahead, but I want to know what's going on in my device. Alright, so next thing we do is we declare a couple of globals. G-force in the X, G-force in the Y, G-force in the Z, rotation X, rotation Y, and rotation Z, and then the calibration values for X, Y, and Z. These are all floats at this point, and they store where we are right now. Now once this is inside of the rover itself, there'll be a communication protocol between the Raspberry Pi and this Arduino in order to call the information that comes from this. I should also note that with the software that I'm showing you here, this is not the only sensor that this is going to be handling. The Arduino is going to be handling all of the sensors for the rover, so I've left some hooks in, so if things look a little funny, chances are that's why it's there. If you have questions, by all means ask. And I also set a global up for the MPU temp. Again, if you have the temperature sensor. If you don't, then this is irrelevant. And loop timer, which we'll get to in a second. So the first part of any Arduino program that we always enter is the setup. Alright, so the very first thing we do, like I do with all of my setups, is we start serial. I'm starting the serial connection at 57600. I'm setting a pin mode for the status pin to be output. If you remember the define up above, the status pin is pin 13. I'm setting it to an output. I'm then turning the LED that's attached to the status pin off, in case it came up online somehow. Actually, for our purposes for this demo, I'm going to take that out. We're going to do a wire.begin. If you put a value in here, that allows this Arduino to function as a slave. And for this example, it is a master. So I'm going to take the 9 out. We're just going to leave that the way that is right there. Then we go into a function called setup MPU. Now, as I said, there's a few things with this particular sensor that are hard to get accustomed to and wrap your head around. So the first thing we do is we begin a transmission to the MPU-I2C address. So we're telling the wire library that we want to communicate with this device. And then we send to this device the registry address for the power registry. Because trap for new players, when this device first comes online, it's asleep. You must access the power registrars in order to wake it up to make it do anything. So we access the power register and we write the power mode that we want to that register. And we end the transmission. Ending the transmission causes it to be communicated to this to the MPU-6050, and the MPU-6050 will then wake up. We set a no sleep mode in that one. I'm going to touch base with, and like everything else, I will put a link to this in the description and on the website. Where is? So as I said, we've written all zeros into the power register, which will cause this device to wake up and not go to sleep. The next thing we're going to do is we're going to choose the scale that we want for the gyroscope on here, like we talked about. So again, we're beginning a transmission to the address of the MPU-1_I2C, which is this guy right here. We're accessing the gyro configuration register. We're writing the values for 250 degrees per second, which are held in this defined value up above. And then we're ending the transmission. That will put the gyro in this device into a 250 degree per second scale. Very similarly, we are once again doing virtually the same thing. We're starting a transmission to this guy one more time. We're telling it that we want to write to the config register for the accelerometer. We're going to write the value to select the 2G scale, and then we're going to complete the write. Okay, so once this section of the code is done, we're fairly confident that this device is set up and ready to go. So we come back to this setup routine. This should actually only be 3,000. So now we're going to delay. And the reason we're going to delay is I have found you get better results if you let this sensor settle before you start taking readings. So we sit for 3 seconds and we calibrate the gyroscope. Okay, so if we go down to our calibrate gyroscope routine, actually let me talk about the read routines first. Then the gyroscope, then the calibrate will make more sense. So once we printed setup complete, we enter into the main loop of the program. Main loop of the program simply attempts to read the MPU. If it can successfully read the MPU, right, it sets up its loop timer and waits the 4 microseconds to generate a 250 hertz cycle through. This will prevent us from doing double reading, which will be very important when we want to make meaningful use of this data. So if we look at read MPU itself, I've temporarily commented out some of the work I've done to make the values that we get meaningful. So if you see some comments in here, I apologize. I wanted to get this video out. I thought this would be a single video topic. As you can tell by the length of this video, it's not a single video topic. So first thing we do is read the accelerometer and read the gyro. Okay, so if we take a look at the actual read functions, once again we begin a wire transmission to the accelerometer itself. We select the accelerometer read register and we end the transmission. Okay, so that sends to that sends to the MPU-6050 that we want to get the accelerometer data out of you. We then request from the MPU-6050 the amount of data that is the size of this register. So in this particular case, we're asking this device to send 6 bytes of data from where we set the register to. So now I have a timeout here in case this ever fails, so that we do have an escape and we don't completely lock up. A couple of the other tutorials that I saw had while we're waiting for 6 bytes of data just sit here, but there was no escape. So if anything ever happened to the gyro or the MPU-6050 and it rebooted, let's say, or it lost power or it browned out and it never sent that 6 bytes of data, we would still be waiting here forever, locked up. And that's a problem in an autonomous vehicle. So we wait 2 seconds for the data to come here. If it doesn't show up, we abandon the read, we don't pay attention to the data, and we move on to the next one. Once we do have that though, we take G-force X and we calculate it by taking the first byte, shifting that left 8, and then adding the next byte to it to produce the 16-bit integer values that represent the degree, or this is the accelerometer that represent the G-force rating on that particular axis. Now, when you first read the data from this device, it's not going to make any sense. It's going to be a wildcard value. That has a lot to do with the scaling. So what we need to do is we then need to divide by the number that the data sheet for this device gives us to bring the scale back into something that is just G, right? Something that is just the force of acceleration. I tend to use a lot of defines and a lot of words in my code. That way I don't have weird numbers. I hate magic numbers. So if you ever want to know what one of these are, if you look up at the defines up above, for example, with this one, 2G scalar value is 16,384. So what that means is down here we take those two bytes, put them together to make the 16-bit integer. Then we divide them by that 16,000 number that we saw up above, which will give us a number in G-forces that is real. And once all three of those are done, we return true back to the calling thing, and we move on to reading the gyro. Now, as I'm sure you're going to notice, reading the gyro is remarkably similar to reading the accelerometer. So once again, we start with wired up begin transmission. We use the address of the MPU-6050. We write the register we want to read. We end the transmission, and then we request as much data as the buffer size is for this, which for the gyro is 6 bytes again. 3 16-bit integers. Again, we have the timeout for the exact same reason as the last time. And we once again take rotation X equals the first byte left shifted 8 added to the second byte divided by the scale for 250 degrees. So if you're going to change the scale that you're using with yours, make sure that you remember to change these as well to be the scale for whatever scale you're using. Wow, that just sounds weird, but yes. And then once again we return true. We print data to the serial monitor and we return. Now, as I said, this whole section here does not need to be anywhere near as complex as it is. But I know I'm going to be handling more than one sensor with it, so it makes sense when you think of it that way. So going back to the calibration for this sensor, one of the things that we do here, right, we enter here, I turn the status pin high so I know when I'm in calibration. And when you're in calibration, you want the sensor to be as flat as possible, right, or as close to 0, 0, 0 as you want to calibrate to at that point. So we tell the serial line that we're calibrating the gyroscope. We start with a calibration of X, Y, and Z at 0. Those are the global values that we declared up above, the global variables, sorry. We enter a for loop, which is I equals 0, I such that maximum calibrate reading number. If you remember the define up above, for me it's set to 2000, so we're going to take 2000 readings, which at 250 hertz is 4 seconds, and I++. So we read the gyro, and then we take the calibration X value and we plus equals rotation X. So what we're doing is we're taking the values that we've read from rotation X, Y, and Z, we're adding them into the calibration X, Y, and Z fields. Then we're waiting here, we're enforcing the 250 Hertz read cycle. So we're stopping for 4,000 microseconds, not milliseconds, microseconds. And then we're moving through. If we fail to read during the calibration, we decrement I so that we don't miss a value. Right, we'll try to get that next value later. Then we take the calibration X value and we divide it by the number of values we took to get the average of those values, and we assign it back to the calibration value. We print them out to the serial monitor. We set the status pin to off, and we start to cycle through the actual running of this code. Now when it comes to printing, that's when we actually use the calibration data. So we have rotation X, which is the last rotation that we read from this device. We minus the calibration X we minus the calibration value for X, Y, and Z in order to get us to stay as close to 0 as possible. There is some fluctuation with this. One of the experiments I'll be doing before the next video is seeing if the higher scale numbers start to lose that fluctuation on the low end. 0.01 degrees per second is not a whole lot out, but I do want to see if I can get it as precise as possible. So as we've said, that's all the code there is to this example. We will upload it one more time to the Arduino. It's done uploading. Open up the serial monitor. It should take about 2 seconds. Yeah, calibrating gyro. And once again, you can see it reading the values out from what it's gotten from the sensor itself. And of course, as I mentioned, I do not have a temperature sensor, so that's why that is there. So we're going to take a moment now and we're going to come back from the desktop. Alrighty. So we're back up from the laptop itself. And we're back into here. One of the things I wanted to mention is that yes, this is a very complicated sensor. And there's a lot more that you can do with it than what I have shown here. I tried to keep it as light as possible to be just what you will need to work with this. However, there is an exhaustive data sheet. I will link to it in the description down below. Feel free to check it out. The next time we get together, we're going to take a look at using the information that we get from this sensor to try and maintain a roll, pitch, and yaw value for the rover itself. Thank you for joining me in the lab. I hope you learned something today. If you haven't already, go ahead and click that subscribe button down below to make sure that you stay up to date with all my content. Once again, thank you for joining me in the lab, and I will see you next time.